Consider its troll comic. What's wrong with it? Of course, nothing should be able to go faster than light, even light itself. So what's wrong here? To explain why nothing can go faster than light and how this paradoxical comic can be resolved, we're gonna have to go back in time a bit. When he formulated special relativity, Albert Einstein began with two postulates. The first is the principle of relativity. That is, every inertial frame of reference experiences the same law of physics. This principle actually was a thing long before Einstein, and I'm certain you've used it before. Say, you have two cars with the slower one in front, and you want to calculate how long it takes for the faster car to catch up. You could work out the problems yourself, it's not too hard, but chances are you're using relativity in some way, by finding the relative velocity between the two cars. Now, the principle of relativity says that the same law of physics applies for all inertial frames. A classic example is throwing a ball forward on a train. The ball is going to travel the exact same trajectory whether you are on a train or not, as long as the train is not accelerating. Obviously, if it's in an accelerated frame, the first postulate doesn't hold. For example, Newton's first law is that if there's no force acting on something, then that thing is going to continue moving the way it does forever. You can see how this is violated in an accelerating frame. The frame is going to see the thing change its motion even though no force is acting on it. What I'm saying is, we're only working with inertial or non-accelerating frame of reference here. The second postulate is what differentiates regular Newtonian physics from special relativity. Galilean relativity, or classical relativity, lacks the second postulate, which is what created the paradox from the comic at the start. This postulate, the speed of light is c, is a law of physics. This may seem like it's out of nowhere, but it's not entirely baseless. It stems from Maxwell's equations, the four equations that govern electromagnetism. It is a law of physics. With a little bit of calculus and algebra, it was shown that electromagnetic waves can exist, and they must propagate at c. Light is an electromagnetic wave, and hence it must propagate at c. So it is a law of physics. And this gives us the second postulate. Okay, well that clears up how it came to be, but what are the implications? Well, the speed of light being equal to constant c, being a law of physics, implies, from the first postulate, that the speed of light is constant in all inertial frame of reference. So this solves our paradox. The light turned on a train is going at c, regardless of whether you are on the train or not. So that light is not traveling past the speed of light. Video over. Wait. But if you're on a train, you'll see the lights move further away from the flashlight compared to being off the train. And I play the animation at the same speed. You can see that the distance do not line up. So by accepting the postulates, which are true, it solves our paradox, but throws our intuition out the window. Let's see what I mean by going over the effects the postulates result in. First is time dilation. I'll explain the math in a bit, just allow me to elaborate. You may have heard this one before. When you see a clock in a spaceship, and that spaceship is going very quickly, you'll see the clock on the ship is going slower than your clock, and a person on the ship would also seem to age more slowly than you. However, the inverse is also true for the person in that spaceship. They would see your clock tick slower than theirs, and you would age more slowly than them. Oh, and by the way, when I say see a clock tick, I really meant the actual time that the clock ticked, not considering the time delay from the light traveling from the clock to reach you. And this goes in both directions too. Whether the spaceship is going towards you or away from you, this slowness factor remains the same as long as the speed remains the same, irrelevant of direction. Let's quantitatively measure this slowness factor. We're going to set up a vertical mirror on the spaceship now. It's vertical in a way that it's perpendicular to the direction the spaceship is going in. So now we place a little laser device on the spaceship floor right beneath the mirror. This device doubles as a detector as well, for when the laser reflects back down, the detector is going to go off. Let the spaceship go at a constant speed v, and we activate the laser. Observe the spaceship's frame of reference. In this frame, the spaceship is still, but the Earth is moving away from it. In here, the laser goes up, and then back down. Call this time interval t prime. The speed of light is c, which here I set to be quite small for the sake of demonstration, and the height of the mirror is, let's say h. T prime here, of course, is going to be 2h over c. That's the time it took for the laser to go up and back down. We'll keep this in mind. And now let's rewatch that, but from the Earth's perspective. You caught that? Here in this frame, the laser moved diagonally to get to the mirror and back down to the detector. Importantly, unlike in the spaceship's frame, the upwards velocity is not c, but rather something a little smaller than c. Now let's say the time interval this time is t. Then the distance the spaceship, and by extension the detector, had traveled was vt, with v being the speed of the spaceship. Then by the Pythagorean theorem, these diagonal lines have the length of square root h squared plus vt over 2 squared. There are two of them, so we'll multiply by 2, giving us the total length of these lines, L. Why is this important? Well, it just so happens that this is the path that the laser takes during the journey. And remember the postulate, the speed of light must be constant at c. It took the time t for the laser to travel this path, so the length of the path has got to be ct. So this sets up our equation. A little bit of algebraic manipulation can isolate the value of t. It turns out to be 2h over c times the square root of 1 minus v squared over c squared. And hey, remember the factor 2h over c? This is t prime. So you can now write a relation between the time interval between the two events in the spaceship's frame and the time interval between the same two events in the Earth's frame, with a major asterisk. I'll get back to the asterisk, but for now let's work out some solid examples. If the spaceship is traveling at 0.6 c, then the time delay factor here will be equal to 1.25. That is, in Earth's frame of reference, the frame in which the Earth is stationary and the spaceship is moving, 5 ticks of a clock on Earth would sync up with 4 ticks of a clock on the spaceship. But in the spaceship's frame of reference, the clock on the spaceship would tick 5 times, where the Earth's clock ticks 4. In general, the t prime refers to the time interval between two events, in the frame where both events happen at the same spot. Whereas t refers to the time interval between the two events for the frame we're currently in, but the two events may happen at different places. This is the asterisk I was talking about. The two events must happen at the same place in one of the frames, and in that frame, the interval is t prime. So we have quantified the slowness factor, but it's still rather unintuitive. Both frames see the other's frame go slower is ultimately what you have to accept, as hard as it may be to visualize. Now, onto length contraction. When moving close to the speed of light, things will have their length contracted in the direction of motion. So a ball moving very quickly would be more like a plate. A spaceship moving close to the speed of light will appear compressed. And this is how you can actually travel smaller distances by going faster. You can reach a galaxy 1 billion light years away in 1 second of spaceship time, but a billion years would have passed outside. Well, let's quantify the quantity. I summoned my good pal laser and mirror, but this time I'm going to set the mirror down horizontally, that is, in the direction of motion. Let the distance between the laser pointer and the mirror when they're not moving be L prime. Once again, we let the spaceship run and shoot the laser. This interval, again denoted t prime, is 2L prime over c. Now let's replay the sequence in the Earth's frame, with the distance now L as opposed to L prime, since we're assuming the length is contracted. You'll see that the laser takes a little longer on its way to the mirror than on its way back, because the mirror is running away from the beam during the first bit, and the detector is moving towards the beam for the second bit. I'll call the time it takes for the first bit TA. During this interval, the distance the laser beam must cover, CTA, is the original distance L, plus the extra distance that the mirror ran away from the beam. That extra distance is VTA. Again, a little bit of algebra gives us TA equals L over C minus V. The return trip is similar. The time interval for this bit is TB, but this time the light has to travel less. That reduced distance is VTB, giving us TB equals to L over C plus V. So, the total time is TA and TB added up, which simplifies to 2L over C times 1 minus v squared over c squared. This is the time interval between the two events in Earth's frame of reference. And this other one is the time interval between the two events in the spaceship's frame. I'd like to add that in the spaceship, the two events again happen at the same place. So the time interval are also related by time dilation. Earth's frame is t and the spaceship's frame is t prime. Combining the two equations together, we have these. Here you can see that the distance is also scaled by the same slowness factor. This slowness factor has a name, the Lorentz factor. It's typically denoted by the Greek letter gamma. When the speed is 0, this factor has a value of 1, and when the speed approaches c, the value of gamma increases with no upper limit. The length of something in a frame is shortened by the reciprocal of the Lorentz factor, meaning as the frame of reference moves faster, the thinner the object becomes. In fact, you may have wondered why I made this video in Minecraft. Well, for one, I typically do Minecraft-related content. But another reason is that Minecraft is heavily moddable. So I coded a shader to demonstrate length contraction. Of course, I turned the values of c all the way down so that you can see that as I move, the length in the direction I'm moving shortens. And it's only in the direction that I'm moving. The perpendicular directions remain unaffected. And if I get close to the speed of light, this kind of happens. Things get so compressed it practically becomes a plane. Alright, let's see some concrete examples. Proxima Centauri is the closest star to Earth excluding the Sun, and it's around 4.2 light years away from Earth. Traveling at 99.9% the speed of light shortens that distance to around 0.19 light years in the spaceship's frame. So while the Earth would find the spaceship reach the star in 4.2 years and a little bit, the spaceship would reach the star within around 69 days. Nice. So that's length contraction, also known as Lorentz contraction. To segue into the next topic, allow me to propose another paradox. I have a really nice car 5 meters in length, and I have a garage that is 4 meters in length. If I drove a car at, say, 0.6 c into the garage, would the car fit? In the garage's frame of reference, the car is moving at 0.6 c. So according to length contraction, the car's length is 4 meters as opposed to 5. So clearly in this frame, the car is going to fit perfectly into the garage. But in the car's frame, its own length is still 5 meters, but the garage's length is contracted down to 3.2 meters, which is far smaller than the car. So in this case, the car is not going to fit into the garage. So does it fit or does it not? This paradox stems from our definition of fit. If the car fit, it means that the front end of the car and the back end of the car are both in the garage at the same time. This is the case in the garage's frame. The event where the front end of the car is just about to leave the garage, call this event A, happens simultaneously as the last bit of the car enters the garage, calling this event B. What I'm saying is, in the garage's frame, event A and event B happen simultaneously. There's no delay between them. But in the car's frame, the front end of the car leaves the garage first, before the back end enters the garage, meaning that event A happened first, and after a small delay, event B happens. What I'm saying is, even though two events occur simultaneously in one frame, it need not do the same in other frames. That means the notion of the car fitting into the garage is frame dependent. This is relativity of simultaneity. Alright, well, let's quantify it. There are actually many ways to get the formula. The most common one revolves around the spaceship and two laser emitters. But we used this one for time dilation and length contraction already, so let's have a bit of a change in scenery. I've already talked about the garage scenario, so we'll work with that one. In the garage's frame of reference, where event A and event B happen simultaneously, the length of the car is equal to the length of the garage, so we'll call this L prime. In the garage's frame, the length of the car is contracted by a factor of gamma, down to L prime. That means in the car's frame, the length of the car, L, would actually be gamma L prime. On the other hand, the garage's rest length is L prime. So in the car's frame, its length would be contracted to L prime over gamma. When event A happens, that is, when the front end of the car is at the end of the garage, A little bit of the car's back is still outside the garage in the car's frame. Simple subtraction gives us how much is still outside. Then, after a small time delay, delta t, the back end enters the garage, and that's event B. Delta t is the time it takes for the garage's door to travel the distance of L prime times gamma minus 1 over gamma at the velocity of v. So delta t is just L prime over v times gamma minus 1 over gamma. The expression is a little messy, so I'll simplify it a little bit, and it's going to give us v over c squared times gamma L prime. So let me conclude this result. In one frame of reference, two events A, B happen at the same time, but are spatially separated by L prime. Then in another frame moving at v relative to it, the events will also be temporally separated by v over c squared times gamma L prime. There are limitations for the formulas we got. This equation for time dilation is only applicable for when t prime represents the time interval between two events that happens at the same place. On the other hand, the equation for simultaneity requires two events to happen simultaneously in one frame. Oh, and I'm going to change L prime to X prime so we understand that there is separation in the X-axis, the axis that aligns with the velocity. So, we're going to form a general formula to find the time delay between two events in a different frame of reference, without the restriction that they happen at the same place or time. Allow me to draw a space-time diagram. The y-axis of the diagram represents time, and the x-axis represents, well, the x-axis. A point on the space-time diagram represents an event. For example, this event happens at x1 and at time t1. And this event happens at x2 and time t2. I'm going to call this frame of reference the prime frame, so as to make it line up with the previous examples. Now, what we want to do is, given the two events in the prime frame, and given the velocity of another frame of reference, the unprimed frame, when and where does event 2 happen in relation to event 1 in the unprimed frame? That is, given delta x prime and delta t prime, what is delta x and delta t? To help with this, I'm going to find an auxiliary event, event 3. This event happens simultaneously with event 1 and at the place where event 2 will happen. So event 1 and event 3 happen simultaneously in the prime frame. So we can find the time delay between 1 and 3 in the unprimed frame by using the simultaneity formula. That turns out to be gamma v over c squared times delta x primed. Additionally, in the prime frame, event 2 happens after event 3 by delta t prime. And they happen at the same place, which allows us to use the time dilation equation. That means in the unprimed frame, event 2 will happen after event 3 by gamma delta t primed. In turn, event 3 happens after event 1 by gamma v over c squared delta x prime. So the overall delay between event 2 and 1 in the unprimed frame would be gamma delta t prime plus gamma v over c squared delta x prime. We're not done here yet. We've already done so much, so we might as well find where it happens as well. That is, from delta x prime and delta t prime, let's find delta x. In the prime frame, event 2 happens delta x prime away from the point where event 1 happened. So I'm going to put a pin on this point and call it point A. In the unprimed frame, this distance is going to be contracted according to length contraction. So in this frame, event 2 happens delta x prime over gamma away from point A. But don't forget that point A is also moving. When event 1 happens, we put the pin there. And then the pin also moves along the primed frame with velocity v. So the distance that point A traverses is v delta t. We already found delta t earlier, so we just plug it in. And the total distance between where event 1 and event 2 happens in the unprimed frame, delta x, is just the two distances added up. Simplifying the terms a bit yield delta x equals gamma delta x prime plus v delta t prime. And so this gives us the equation that relates spatial and temporal displacement between two frames of reference. This formula is known as Lorentz Transformation or Lorentz boost. Hendrik Lorentz was the theoretical physicist who came up with the transformation, but under a different premise. He was under an assumption regarding a luminiferous ether and ended up with the same result. I'm not going to go into the historical detail, but the bottom line is this transformation can be used to tell when and where something happens in one frame, given the when and where in a different frame. With Lorentz Transformation in mind, it is time I bring forth another paradox. In fact, this paradox is very similar to the opening troll comic. Assuming you have a friend running on a train. That friend of yours is speeding at 0.6 c relative to the train, and the train is also going at 0.6 c relative to you. Is your friend going past the speed of light in your frame? If you add up the velocities naively, you get 1.2 c, which is clearly faster than the speed of light, and well, it's wrong, we don't really add up velocities like that here. The results are fairly accurate with smaller velocities, but as we get closer to the speed of light, we're gonna need a new formula. Let's say your friend's velocity relative to the train is denoted u prime, and the train's velocity relative to u is v. We can use Lorentz transformation to find u, your friend's velocity in your frame. Let's say your friend shouts twice, and the time delay between the shouts in the train's frame is delta t prime. So obviously on the train, the places where they shouted are separated by delta x prime, which is equal to u prime delta t prime. Now we want u, delta x over delta t, that is the distance between the shouts over the time delay between the shouts in your frame of reference. So the Lorentz transformation which we derived earlier comes in clutch. Again, there's a bit of algebra, but you could also work this out yourself. Whenever we see a delta x prime over delta t prime, we can change that to u prime. It does look a little messy. Ultimately, it simplifies to this expression. If v and u prime are relatively small, it approximately equals to v plus u prime, as we see in everyday life. But for our example, at 0.6 c for both u prime and v prime, the velocity in your frame of reference becomes around 0.88 c, as opposed to 1.2 c we got earlier. As one last note on this velocity addition, let's go back to the troll comic. To the person on the train, the light travels at c, so u prime equals c. Now, according to our velocity addition formula we got, it doesn't matter what v is. If u prime is c, then u is also c, meaning that light traveling at c on the train also travels at c outside the train. This is consistent with the established postulate, and thus it solves our paradox. Well, that was a pretty lengthy video. There's still much detail I want to go into, but I just can't fit them into this video considering how quickly I'm able to make videos. If you are interested in some more insight, I recommend checking out some courses on the topic. If I remember correctly, Khan Academy has one. This video is made for Sum 4, and I want it to act as a first exposure to many people to special relativity, as there are lots of Minecraft players who don't know much about special relativity. And yeah, I hope you learned something and I sparked some curiosity. If I had made any mistake, please point them out in the comments, and if you need any clarifications, do ask them in the comment section too, and I'll try my best to clarify. So please like and subscribe, and have a good day.